Hello, I'm Madis, and I worked on the attitude and orbit control system sensors in the summer. I started off with some driver refactoring, trying to make them more usable, like to communicate and set up the sensors. Then we went to Tallinn with Henrik to use the sensor board on a small Xbox controller controlled tank, and that was pretty awesome. Then I got the newly made onboard computer system prototype board to use and to test it. After that, I had to design new AOCS prototype boards or toter boards for the OBCS board. And lastly, I attended the FPJ summer school in the last days. And refactoring in this case means that before there were only like write and read functions for each sensor. So I don't know if you can see any of the code, but on the left side there is just used a write function, and there is some random hex value written every time to somewhere. So you always have to look at the datasheet, like what has been done here. So it was much more simpler to make separate functions for every sensor function, to change it like logically without peeking at the datasheet every time. And now these drivers, they're on the old AOCS prototype board and are to be ported to the new one. Yeah, Tallinn trip, we put our sensor board on that thing. It weighs about a ton and it's really agile. And we wanted to take the data and use it in our particle filter and to just analyze it and everything. And we did some data analysis, looking data, and we had a great plan to actually compare the data to a video we took of that thing writing at the same time. But Hendrik lost his phone. Now the OBCS board has a F7 processor, and I'm using the STM own HAL generated with CubeMX. But later this board will have SCube HAL on it. And I went through real-time clock. I tested the communications, and I got communications with the real-time clock, the temperature sensors, and FRAM. And I was debugging the AOCS daughter board, and I could only get the connection with one gyroscope. There are two gyroscopes, one magnetometer and accelerometer, but out of all of them I only got communication with one gyroscope. And why I didn't get the connection with the other gyroscope, turned out that after a day of debugging I discovered that the board had other side as well, and there was no sensor on it. Yeah, and this most of the sensors were old, as in they're not correct in our case, so a new AOCS board had to be made. And there's still I'm still bugging the MRAM part. And the AOCS total board consists of 4 sensors, not including the temperature sensor. It has 2 Bosch gyroscopes, a magnetometer and an accelerometer. That's the last one without a name. And yeah, it's an upgrade from the last AOCS total board. And they have been soldered now that when I've been away, and are waiting for me. Thank you.
How were these sensors chosen?
I did a bachelor's thesis on a selection of sensors that were on the original ASS prototype board, and ran some tests in the thermal chamber and on routing convention and stuff, and finally chose these ones.
Yes, this Milgram visit sounds very interesting. Can you tell us more about it?
No.
What data and how much did you gather?
So
Did you break anything?
did I break anything?
I don't know, it's a military thing.
I hope I didn't.
Good.
But yeah, we got the sensor data from accelerometer, gyroscope, and magnetometer. So everything that's also on the satellite. And
how much data did you gather? Maybe time period? Or
10 minutes. We did 2 runs. I think they're both like 10 minutes or so.
Okay, thanks.
What are the functional results? How well the sensors perform, or were there problems?
You mean on the Milram?
Yeah.
Well, it's hard to say because we don't have the video to look like what really happened. But they remember anymore. I think they showed some more noise, a little bit more noise than usually. But also the Milram machine was like, so that kind of makes sense.
I like the sound effects.
Other questions? Okay, thank you, Alex.
Good. All right. Hey, I'm Robert. My supervisor is Hendrik, and I'll be talking a little bit about the Kalman filter. So, here we go. So, first of all, I would like to say what we should think of what a state is. Usually, what a state is we're, for example, tracking an object. Let's say the satellite, because that's what we're making. So, and in the state vector, we have its position and its velocity. It's a very simple example. So, and usually we have some sensors on the satellite, which can either directly or indirectly tell us where the satellite is. Of course, with some errors to it. And we also have a mathematical model through which we can predict the next state of the satellite from the previous state, like Johanna already said. And the filter, what it does, it combines the 2 results based on their errors. So let's say that the prediction we think has a bigger error than the measurement, then we take more of the value from the measurement and less from the prediction, but we still use both of them. And in the end, out pops a better guess for where we think the state is now. So the best thing, to really understand it is, I think, through like a simple example. So here we go. So we have a circle and a square, and the circle is inside the square. And now we take the ratio of the areas. The ratio in the end is going to be pi over 4. I mean, I think it's pretty simple for us to understand where it comes from. And so now what we should start doing is throw in the square a bunch of random points. And then we measure how many of them points are going to land in the circle and how many are just in the whole square. Why is that? It's so weird. Alright, well, whatever. So here is in the case, in the limit, where the points in the square are approaching infinity, then this ratio of points that land in the circle divided by the points in the square is going to approach pi over 4 also. But we can't really pick an infinite amount of points, obviously. So, also, yeah, so pi, this is just rearranged the last equation. I hope you can understand that. So, but yeah, we can't pick an infinite amount of points. That's impossible. So let's say we pick 1,000 points. So the pi is going to equal 4 times points that landed in the circle divided by the points in the square. Well, plus the points in the square is going to be 1,000 because we're picking 1,000 points, right? Plus an error term, because it's not going to be precise because we're not picking an infinite amount of points. So therefore I defined the measurement to be that. And here I give you guys a little example what the measurements look like. I write a little Python program that did it for me. So yeah, so pretty close to pi already, right? Not really. And here's a graph. So the orange line represents pi, and all of these little squiggly lines are the measurements. So you can also think of it as like a signal with just a bunch of noise to it. And so what does the Kalman filter really do? It is an iterative process. So we have to start. It's like a machine. You got to start it somehow. So you put in some you have an initial condition basically. And for our initial condition, first we have the zeroth estimate, which is the very first estimate. And usually for that, there's different type of methods, but we kind of know what we're dealing with. It's pi, so I just guess 3, for example. And the first measurement is 3, did I use comma or point? Comma 128. Then the error of the estimate, I put it equal to 0.0,15. And the error in the measurement was, as you can see also in the last slide, like the biggest error is somewhere like about 0.2. So that's where the error in the measurement comes from. That's why it's 0,2. All right, so the first step, what we do in the Kalman filter, we calculate the Kalman gain. And this is going to give us basically, as you see, we take error of the estimation and divide it by the sum of the errors. And I'm also, giving you a sample value from these actual numbers. And here it is 0.429. So the next thing, we calculate the new estimation. So therefore it's estimation 1. And as you see, it's depending on the last state also. And so it's, in the end, what it is a weighted average of the measurement and the last estimation. So when you plug in the values and you get to the third line here, you see it's 0,471 times 3, which is the estimation, plus 0,429 times the 3 point. Why do I have points sometimes? That's really embarrassing. Sorry about that. It means the same thing. So that's the measurement. And then for new estimation is 3,055. And also we need to know the error of the new estimation, and that we calculate through this this formula. And as you see, the error, after each iteration you do it, the error gets lower because the Kalman gain is always going to be somewhere between 0 and 1. So therefore the error of the estimation always gets lower. And hopefully the Kalman filter converges to the right value. And the next slide is actually going to be a picture of how it worked for this example. So you see, the Kalman filter's estimation is the green line. So you see that over time it does converge to the right value of pi. It's it's a bit off at first and then it converges. All right, second example. So we're dealing with the satellite, right? So it goes, almost in a circle. So these two functions represent circular motion mathematically. So I have a little video here for it. Yay! It makes a circle. But we actually, in real life, we can't see that. We don't really know where the satellite is. So now we're gonna have to use the sensor data, right? And for this example, from the sensor we get the measured value for the y coordinate, the measured value for x, and then also the velocities in both directions. And I hope you guys can see them. Now we're also going to see what we would see through the sensors, and it's really noisy and horrible. So can you see the blue dot a little bit jumping around there? Yeah? No? Not really? Okay. Well, it's basically what it does. So here's the circle, right? And the noisy data looks something like this. It just like jumps around here. It's like, that's what we get. It's really bad. And so what we need to do is we need to know a little bit about the motion, right? So we make a mathematical model for it. So here we have the function that describes how the particle or satellite is moving in the y direction. And we calculate some derivatives so we can get a third order Taylor series for it, for the prediction of the y. And I hope you guys are familiar with the concept of the Taylor series, right? So this is what I'm using in the model for the next prediction of y, and if you take the derivative of that respect to delta t, you get also what you would use for the prediction of the y velocity. And the same thing goes for the x coordinate. And here's now you see how the Kalman filter is tracking the particle or the satellite. So again, you see it's a bit off at first. It is the bright green spot basically, and over time it starts to track it pretty precisely. And all it's doing is just combining the measurement data with the predicted mathematical model data, and right now it's already pretty nice. Yeah, so that was it. I hope you guys enjoyed it. Oops, it started all over again. So, do you have any questions?
Yes, sir.
Do you know how the initial estimate will be taken for the satellite?
For the satellite? Actually, I do not know how that would be done. What I heard from Hendrik is that we know, like, basically for the position of it, we know like roughly where it's going to be, but the error for it is going to be like plus or minus 10 kilometers. Oh, Johanna, yeah.
About the phi example, what did you use as the mathematical model in that example?
For that, actually, that's a good question, because there was no mathematical model needed, because what we were tracking is just an object that sits in one spot, basically. It's just a constant. So for the next prediction, I just used old estimation, because it stays in one spot. Yeah.
Actually, I have two questions. So, if I understand correctly, you have a mathematical model which makes predictions and then you compare them to the actual observations. So, why wouldn't you just take the average of the value of all the measurements that you've taken up to the point and just do a weighted average from the errors of the, basically the measurements that you have with respect to the model?
Wait.
So, like, why is the common method
Okay. Well, it's needed because for what you just described is basically people do it through like least squares regression line, right? But what we need is like at the next time moment, we already need to guess where the satellite is. But for your method, we would actually need to let the satellite go around a couple of times and just collect data and then put like a line through it, right? But we need to know at every time step where the satellite is, so therefore we can use that method. But it's also very effective.
Okay, and another question in detail, students you stopped at the third term, is there any reason for that or was it just for precision?
Well, that basically gives enough precision, like you saw, for this problem. There was no need to go any further. Actually, I could have even left out the third term and it would have still been fine. Yeah.
How did you generate those points to be placed into circle and square?
How did I generate it?
Yes.
I used the Python code, basically. So I had a random function that picked the points out of the square, and then basically, let's say that I had a circle, right? And the circle was defined like this. So if the point that the random function, the generator gave me was, for example, I don't know, 1, for the x it gave 1, right? 1, what is that? That equals 2. That is bigger than 1, therefore it's out of the circle. And that's how the code was checking it.
So for the 2D example, we assumed measured states were the position and the velocity, I think. But I think
Sorry, I can't hear you, sir.
I'll speak for that. So for the 2D example, the assumed measured states were the position and the velocity. But I think for our satellite, the velocity is not a measurement, is it?
I don't think it is, yeah. I mean, I'm not sure, because first of all, we would actually not even be using regular Kalman filter for it, and I'm just in the process of learning it. So in the end, I can help out Hendrik with writing the actual code for it. Yeah.
Okay, thank you, Robert,
Yeah. You're welcome.
for the
Okay. Hello everyone, great to see all of you. Before I start my presentation, I want to introduce myself. My name is Petris Vitans. I'm from Mansfield University College. My supervisor was Artus Obinans. So, and the topic of internship was development of electrical power subsystem for educational CubeSat model. Speaking of CubeSats, they are a class of siege spacecraft covered in nanoasteroids. CubeSats are built to standard dimensions or units of 10 multiplied by 10 multiplied by 11 centimeters. They can be 1 unit, 2 units, 3 units, 6 units, or larger if it's necessary, and typically weight less than 1.33 kilograms per unit. And a CubeSat consists of subsystems such as payload, attitude determination and control system, onboard computer, communication system, electrical power systems, of course, solar panels and antenna. Speaking of goal, the goal of internship was to continue the development and testing of EPS, which the author has developed as a practical part of his bachelor thesis, to make enhancements for it. About the tasks, the first task and most important was the electrical power subsystem testing. Literature studies, of course, making of enhancements for the electrical circuits of electrical power subsystem, designing and prototyping of printed circuit boards for testing purposes, programming and debugging with Texas Instruments Launchpad, building and testing of solar panels for CubeSat model, and of course, in the final week, user manual making for electrical subsystem board. Speaking of the structure, electrical power subsystem includes functions such as LT harvesting part, which consists of solar cells and maximum power point tracking for each axis, main power bus, batteries, and the charging system with protection against the discharge and over voltage and short circuit. Of course, power distribution part, which includes 3.3, 5, and 12 volts voltage regulators. Of course, protection against short circuit and over voltage in there. And of course, in my system, there is an independent temperature monitoring solution with a microcontroller unit based on MSP 430 series microcontroller. So, speaking of EPS testing, it started with battery charging. I use two different methods. The first one was I use a regulated power supply for battery charging, and in the second attempt I used solar cells. Speaking of first test results, the test results showed that the dependence on load resistance for 3.3 output voltage is really high, and it produces some problems in my system. So, as you can see in the chart, the load resistance, when it's lower than 30 ohms, the output, the voltage regulator can produce in the output the necessary voltage. Theoretically, it must produce 3.3 volts in the output till the load resistance is lower than 2.75 ohms. So, the said problem is with 5 volt output, there must be produced at 5 volts in the output till the load resistance is lower than 5 ohms, and 12 volts till the load resistance is lower than 24 ohms. It could be explained with insufficient input power, because you can produce higher power in the output than it's in the input, of course. And one of the explanations, what explains the situation more, is the solution for 12 volts power supply. The regulator wasn't good. That's why I found something better. Speaking of second attempt, when I used the battery voltage as the input power, and of course current from the dependence on load resistance wasn't so big as it was before, but still the voltage regulator couldn't produce necessary voltage till the load resistance is lower than 2.75 volts, and same for 5 and 12 volts. So one of the experiments what I did after it was effectiveness dependent on load resistance. As you can see in the chart, the curve shows that effectiveness is in range of from 60.5 to 76.8%. It means it depends on load resistance. As you can see, to improve effectiveness of power system, I must use higher power in the input, or I must replace previous solution for 12 volt power supply with better solution, which you will see in the next slide. Speaking of it, I chose it and then I tested, and then I compared the results, this with previous, and this solution was better. So I decided it include in the list of enhancements. Speaking of next enhancement, it was a current limiter for the protection against short circuit for 12 volt power supply. I decided to use it in my solution for it, so I tested it and it worked. But speaking of power monitoring and LC low pass filters, I added both of these in the list of enhancements because they were necessary for a good solution for electrical power subsystem. Before it wasn't there. Speaking of test results, they show me that previous solution, speaking of what I mentioned before, wasn't so good, but I didn't test it with solution of protection, so I must repeat the test. Okay. Then next, speaking of prototyping, for each of tests, I prototyped and designed a printed board, which I made in our prototyping laboratory by using Mion technology. So when all of these circuits were tested, then I chose the best solutions, which, as I mentioned before, I included in the enhancement list. For testing purposes, in all of the experiments, I used a breadboard, PCB multimeters, a regulated power supply, batteries, solar cells, or of course electrical power supply system. What can I say? Our experiments have done now about 30, and they were a good experience for me. Yeah, how you can see prototypes. And yeah, then one of the tasks was building and testing of solar panels. I do it because if you want to produce necessary power and you must use some better solution than this in the table. Okay. My solution was better when I compared it to original solution. I compared the same sizes and I compared the power. As you can see, my solution was better because my maximum power was higher. For testing, I use radiation of the sun because it's a real environment for them. Yeah, then one of the tasks was programming and debugging with Texas Instruments output. Speaking of it, before I started programming and debugging, I read about free reactors and Texas Instruments outputs and programming with them. The internship showed me that free reactors can be used for strictly managed hardware. For example, it could be used for shared peripheries to avoid from some collisions of in electrical power subsystem. Okay, and then speaking about problem solving, the methods that I used for problem solving were reading about things I didn't understand for, repeating tests and reconstruction of circuit. The biggest problem in my traineeship was about common mode voltage for differential amplifiers, which is the difference between power supply and one of the input voltages. I didn't understand before why in the output of differential amplifier is incorrect result of current measurements. And of course, yes, speaking of enhancements, enhancements were LC robust filters, better solution for 12-volt power supply, high side currents and subwoofer for power monitoring, better solution for battery charging, which I minimized it from 4 cells to 2 cells. And the final task in my traineeship was I use a manual mapping for a power supply system board, which consists of overview, power budget, protection solutions in FIS, power supply, battery charging, test points, temperature monitoring, test results, enhancements of power subsystem, board dimensions, board layers, and schematics. Speaking of summary and conclusions, the test results show me that there are a few things which must be changed for the better solution of electrical power subsystem. The next step for the development of electrical power system should be a designing and testing of electrical power systems PCBs with the included enhancements. And of course the internship was a great experience with the added value. So here's the literature I studied, and before I finish my presentation I want to express a gratitude to SpaceTEM and Interreg, and of course my supervisor Arthur Soldant, and of course thank you for your attention. Any questions? For the system?
For the load itself, did you actually need
where I get that load resistance?
No, well, why do you need to go with a higher load, so less resistance now?
If I was right, then I must produce the output for 3.3 power line, the power which is equal to 3.96 watts. It means current must be which flows through load 1.2 amperes high. For example, for 5 volts the same, it means 1 ampere through the load resistance, and 0.5 for 12 volts.
I have a second one. About the solar panels, like they definitely wasn't the same ones to be used. So what did you have possibility to check each parameter to actually see that your design was actually better than the previous one?
Speaking of it, sorry. Okay, you can see the original solution for educational CubeSat model, and my solution I use 4 solar cells which I bought from eBay. That's because it's cheapest how to build it. Then I measure, as I told you before, both of these solar panels, original solution and my solution, and then I compare the results, and I come to the conclusion that my solution is better.
It was just, I was thinking that over the time this technology had grown.
Yes, it depends on the parameters such as temperature, radiation of sun, for example.
And how did it perform when you had like different angles with MPPT, or like how MPPT performed with different angles or any kind of
it tries, and maximum power point tracking is used because it tries to fix point in same position.
I'm just asking what were the results.
I didn't test that.
I suggest that the units of power is in the milliwatts.
Yes, in milliwatts. Of course, yes. Thank you. Yeah. My mistake. Yes.
In the last picture somewhere, like, yep, have you manufactured that board?
What?
Have you manufactured that board?
Yes, as I said, in board layers you can see all of the details about printed board if you think about it.
What company did you use?
What component?
Yeah, to manufacture.
Company?
Yeah.
Branner, yes.
What wasn't it too expensive for you?
It was the fastest way, and it wasn't so expensive because, how to say, the deadline said you must think faster than ever before, and then I decided to order from them.
Thank you, Ben.
Okay.
So, the next one is
Okay. Hello everyone, my name is Anni.
And I'm Rudolf.
And we did our internship at the Baldon Observatory in Latvia. And our goal was to find new carbon stars.
So, all right. So before we talk about exactly what we did, we'd like to speak a little about what the observatory does overall. So as we already mentioned, one of the main goals is the search for new carbon stars. And the reason why we do that is so we could update the current catalog of them, because all of them still haven't been cataloged yet. Another thing is that there have been, the observatory used photographic plates for a very long time. Currently it's moved on to electronic data storage, but it still has a very large number, 25,000 photographic plates, and many of them still haven't been analyzed. And the reason why we like to analyze them is because they might contain interesting information. For instance, stuff about small bodies within the solar system, so things like asteroids, maybe comets. And the reason why we're very interested in those could be possibly because we really want to be sure that they don't unexpectedly hit Earth, or we want to be sure about their orbital parameters so that apocalypse doesn't happen, basically.
So, we set our goals for the internship. We wanted to learn more about the astronomy and gain skills in photo editing and data processing. And data processing is basically what most of astronomy is about. And we wanted to find at least one new star that wasn't found yet.
So,
and also, my personal goals were to do a bit of observations with a telescope, because I always wanted to work with a telescope and do something with it. And also learn a bit of Latvian while I was in Latvia. So I know a couple of words. I know paldies, I know sveiki, I know sometimes, of course. And I also learned the numbers, so I'm pretty okay with at stores and everything.
I wanted to interact with and understand telescopes slightly better, because I still hadn't had any experience with them before, and also wanted to do some astronomy related programming, so data analysis through that as well.
So first of all, what are carbon stars? Carbon stars are usually defined by stars that have more carbon than oxygen in their atmosphere. So that makes them very big, because they're nearing the end of their life, and they're also very red. And the reason that they're big also makes them very bright, almost 100 times brighter than the sun. So since the carbon stars are burning helium mostly into carbon, then they are also much cooler than the main sequence stars.
Right, so how do we process the work about carbon stars? So first of all, we make a long exposure photographs, which are taken by the telescope, of course, and then we try to find a carbon star. So for instance, okay, this is important.
Okay, like
You can take
this one. I'm not sure how it works.
What's this one? This is something?
Oh, this one?
Yes.
Okay, right. So, how do you use it? Right, okay, so this button. Okay, so this in the middle would be the carbon star. So you might say that, well, these don't really look like stars, which you would usually see through a telescope. Like usually stars would be just points. But if they were just points, you couldn't really tell like their spectrum and what they're made out of. So instead what we do is we put a prism inside the telescope and pass the light through it so it gets dispersed. And so what you can actually see here are, for instance, like you can see the bands, for instance, through oxygen or some carbon-nitrogen compound, I think there. And so you can identify the spectrum, and from that you can actually say that they're carbon stars. So after you've identified a carbon star, you basically get its exact coordinates by looking at a star map. For instance, the most widely used star map is Aladdin. And so you just like use a picture editing software where you put one of the pictures on top of the map, and so you compare them, and that way you can get very exact coordinates of where the star actually is. So basically, because a very large number of potential carbon stars have already been identified from spectral analysis, but it's been a very crude, well, like the spectral analysis has been done on a very crude level, because here you can see on this axis you have the color index of the star, which is basically just the amount of intensity it has at one wavelength minus the intensity it has another wavelength. And over here you have the percentage of stars that are there. So on here you have carbon stars, which we're interested in, and on here you have M stars. And as you can see, there is significant overlap. So for instance, if you have something around 4, you can be fairly certain that it's a carbon star. But basically everything around here, where you have the majority of them, you can't really be sure whether they're carbon stars or M stars, so you need to manually check them. And that's why, because because M stars are significantly more widespread in the universe, the catalogs are like quite imprecise. You usually have a ratio of somewhere around 40 M stars for one carbon star, so you really need to like check them a lot. So in order to do that, I developed a program which basically searches for the optimal coordinates which you should search at. So the telescope has two 1 degree by 1 degree matrices, and hence it has a composite and a wide angle field of view. And as a result, it can observe potentially a very large number of those objects that we think are potential carbon stars. So maybe even something like 100 in a single shot. So in order to make the fewest number of measurements, you can create an optimized sequence of observation coordinates. And so basically how I did it is I made a linked list of these coordinates, and in that way you can minimize the amount of time you actually need to observe all of them. So this is a graphical representation of the program that I wrote. So you would start somewhere around here. So the observation point is in the middle, and these two are the CCD matrices, which are actually observing the stars. So you would start somewhere around here, and then you'd iterate through the whole field of view. And as a result, you'd make this linked list where you have, for instance, 25 unique stars here, and the coordinates at which you observe them. Then it's linked to the next point where you have 5 unique stars with their coordinates and etc. And for instance, if I wanted to add this point, I would add it here or here. It doesn't really matter. So it would be a sorted linked list, and you would be sure that the sequence that you get is the optimal one. And as a result, you minimize the amount of time that you need to actually make the measurements.
Yeah. So from the picture you saw earlier about this long exposure images of carbon stars, from that picture I got the pixel density graph for the carbon star. So after putting the graphs through some programs, like I removed the background noise for the first thing, and then I normalized the graph. So I actually got the wavelength of the carbon stars. So here you can see 3 carbon stars and their graphs, and you can see as the wavelength is more in the red area of the spectrum. Also you can see the carbon, nitrogen and oxygen bands on this graph. And then I found the distances of carbon stars. I found the distances in 2 different ways, by the method of Aronow and the method of Schlegel. They are slightly different from each other, and Aronow is more precise in closer stars and Schlegel in the further away stars. And on this graph you can see how many stars were at certain distances. So also I found the effective temperatures of stars using a graph that had been developed by a previous research in this area. And that graph had, there was a relation between the gradient of, like, wait, how does it work? This one, okay. Between the gradient between those 2 points and the temperature of a star. And by using this relation, I was able to get the temperatures. And then I also found the luminosities of those stars. And here is the Hesburgh-Russell diagram showing the things I found. You can see luminosities in the left and temperatures up there. So the carbon stars would be around the giant branch of red stars. And also you can see the carbon stars we found in the Cassiopeia constellation. I don't know if you can see some green dots in there. The green dots are the stars that were not in the catalogue, so they might be possible new carbon stars. In total we found 6 possible new carbon stars. And also I put the stars on our galaxy map. So you can see that they are mostly in the Perseus and outer arms of the galaxy. But yeah, since we're looking in that direction mostly.
Right, so before you make the observations, you actually need to check that the telescope is in order. So because the nights in summer are too bright to actually make observations, that period can be used to actually like repair and check whether the telescope is working properly. So what I did was I basically, you can see in the picture on the right, I made the picture from the inside of the telescope where I cleaned the mirror and the lens using an ethanol solution. And we also checked whether all of the cogwheels and mechanisms inside the telescope are properly working as well. So,
and yeah, Rudolf was sadly away but we got to do some nightly observations with the telescope as well. So that night we observed 23 carbon stars, and we did it until like 4 AM, something like that, yeah. So this is me by the big telescope.
Okay. Thank you for your attention.
So I have first question. Maybe I missed it. You had these M stars. You had the slide about C stars and M stars.
Yeah.
What are the M stars?
Basically, all of the stars are classified by their spectral class, which is basically related to the temperature that they have. And M stars are just a different type of a spectral class than C stars. They're related quite closely, but they are still distinct stars, and we're only interested in the C stars as a part of our research.
Okay. Can I have another?
Yeah, of course.
You had this example picture with a long exposure time, and the stars were stripes there.
Yeah.
Yeah, but that's not because of the long exposure time. That's because you want to see the spectrum of the star. So as the light enters the telescope, there's a prism, and that prism splits the light into its spectrum. So you can actually see like in the intensity at individual wavelengths, and you can identify the bands. That's not because of the stars moving on the sky.
Okay.
Yeah.
Thanks.
Okay, 2 questions, but I will ask already one minor. But basically, the easiest one is I was with the one last slide where you were doing the cleaning of the mirror.
Right.
What do you think? Can you create problems with this process by doing it, like cleaning it with anything, be it scratches or anything?
Right. Yeah. So there will be some small-scale damage, but generally, since the telescope is in an atmosphere and the atmosphere isn't perfectly clear, you will have residue. You will have some residue basically forming on the mirror, and that's like you can't really do anything about that. So the damage that you do by cleaning it is less than the like obstructions that residue would cause. Therefore, it is beneficial to clean it anyway, even though it might cause some small-scale damage.
Have there been measurements about this?
I don't think there have been in Latvia, but I presume that somewhere else there probably have been. I can't answer that, sorry.
Because as far as I know, in Tartu Observatory's mirrors So I'm just wondering, is it like how it affects scientific data?
I mean, even if the mirror is somewhat damaged, it generally doesn't tend to like out-focus that much. The residue is like a lot more damaging. It is probably preferential to like do what you say, but I'm not sure that we do that in Baldona.
Thank you. The next one is
Oh, thanks. Hello. My name is Felix, and today I'm going to present to you the VLBI web application that I have developed over this time during my internship. So, the goals of this internship was, of course, for me to learn as much as possible about VLBI, what it is, what it stands for, create a VLBI web application, that works both in non-real time and in real time. So let us proceed. We'll start by introducing what is VLBI. It stands for Very Long Distance, Very Long Baseline Interferometry. As you can see, there are two telescopes working together, and the distance between them is called baseline. And what this technique does, it essentially determines position of cosmic objects, and it does so with very great precision. So it's a precise technique. Instead of building one large telescope with diameter 1 kilometer or even more, you could just allocate many different telescopes at great distances, and this would produce the same effect. So the greater the diameter of the telescope is, the greater the precision. And in order to determine the position of cosmic objects, you need to correlate these waves emanating from a cosmic body and received by both telescopes. And there is a specifically designed software tool which is called a Software FX Correlator. And this correlator takes two files as parameters, which I'll talk about. VEX file, which has the following parameters, such as, of course, the name of the experiment, the scan section that defines scans of one particular experiment, start time and end time of each scan, and stations that participate in that experiment, and of course the channels. And the antenna block defines the setting. It describes the information about a particular antenna. For example, in Cambridge is defined as CM, Effelsberg as EF, Ventspils as VE, and so on and so forth. And there is, of course, the VAX file, which is essentially an extended VEX file, which has three more parameters: the Earth orbit position block, tape block. The tape block essentially contains start time and end time of each session, and the clock block, which defines the start time and end time of each station. The second file taken as a parameter is a control file, which defines settings under which the correlator runs. The control file is essentially a JSON object file. For those of you who don't know what JSON is, it is a standardized web technology which stands for JavaScript Object Notation. So it's pretty much just standard. And it contains SFXC instructions such as integration time, reference station, cross-polarization, and number of channels and other parameters. And oh yes, here's an example of a control file, and don't ask me why it looks so ugly and has so many unnecessary spaces. Actually, there's a story behind it. So when we implemented this function that generates the control file, we imported a library that alters the JSON object, and it added some unnecessary substrings to the object and unnecessary brackets, so I had to write a string parsing algorithm which removed those unnecessary brackets, and so it left these empty spaces, and it looks ugly, but it works. So if it's ugly but it works, it doesn't matter. Oh yes, one more thing. The correlator requires time delay files. As you can see in this diagram, there is a time delay between two telescopes. The wave arrives quicker at the telescope on the left, and sometime after that it arrives also at the telescope on the right. But you, of course, can compute this time delay and thereby successfully proceed with correlations. And the correlator outputs one file which contains data about the correlations, which is called a call file. It also needs to be decoded. Yes, on the right, this is not a call file. That's just an example of a plot image of correlation. And before the web application, the SFXC launching process was as follows. You had to first of all launch it manually, which is not automated. You could not so easily launch it remotely because you had to be within the local area of the local network of the correlator, and you cannot automatically convert VEX file to a VAX file. Oh, this was not automated. So what we came up with during this internship is a web solution which allows to remotely launch the SFXC. It is automated. It is quite easy to use. It's also secure because it restricts users with unauthorized access to launch the correlator. And here's how it works. We start by uploading a VEX file into the web server, and then the application checks whether this VEX file contains errors. It first of all checks whether this file is saved as VEX. It cannot be as some PNG file or some other file. It has to be VEX because that makes sense. A file cannot be empty, and finally, a final verification step is sending this uploaded file to the web server and then extracting those parameters I mentioned in one of the first slides. And if one of those parameters is equal to null, the VEX file is invalid, and the web application notifies the user that this VEX file is wrong, and you should re-upload the VEX file. Start it from the beginning. Then we proceed to the creation of a control file. The data is extracted from the VEX file, and some parameters are extracted from the VEX file, and therefore the control file is created, but other parameters you have to add manually, such as number of channels, and there are also restrictions that number of channels cannot be any other number than 2 to the nth power, well, base of 2 number. So if you enter 3 or 7, this will be wrong, and the application will notify you that the number of channels is wrong, and then you upload both files to the correlator server. Then a script within the application launches the SFXC remotely, and then it waits for the correlator to terminate, and it sees the return status upon termination. And if the SFXC returned non-zero exit code, it could be 1, it could be 2, it could be 127, depends on the error, then the application stops and notifies the user that something is wrong and displays the error message. It could be, for example, a segmentation fault or something else. And if everything is fine, if the termination status returned by the correlator is 0, then the core file is downloaded to the web server, and the data is extracted from the core file. Data is extracted, and plot images are generated from the data. And then the user can view these results. Yes, this one is actually one of the examples generated by the application forgot to mention this. And well, that's it. And in conclusion, I would like to say that there were things that that I successfully implemented, that there are things that could be improved, and there are things that unfortunately we did not complete. And yes, there is a working web application, which you will see in the next presentation. There is automatic VEX and control file upload, and there is automatic conversion from VEX to VAX, and automatic data extraction from core files, which is also done. And for now, the only thing that is incomplete is real-time data processing. So I believe that's it. Thank you for your attention. Questions, please.
So you said you need authorization to get access to the application. How does that exactly work? Or who is it intended for?
The administrator is in charge. The administrator can create new users, and basically that person defines who can launch the correlator and who cannot.
And just like you mentioned, it's VRAC, or is it like your company or what is it?
It's VRAC.
Okay. So VRAC, the two
Yes, this institution is responsible for this.
Okay. I mean, you can do VRAC by VRAC, right? That's what I would like to also.
Technically, yes.
Is there a point to it, or is the big baseline too small?
Excuse me?
Between there's the 16 meter and the 52 meter dish. I mean, is the baseline long enough to get that could be on the or something there between two stations?
Not really.
Okay, that's good. Okay.
What telescopes you have selected now?
What do you mean now?
Are doing VLBI?
Well, we're not in the process of an experiment, so I have selected no telescopes.
Oh, okay. But will you be later able to just select like 2 telescopes?
You can select 2 or more telescopes. You can select any number of stations available.
So you have all the telescopes in the world and the application is choose?
Well, only those mentioned in the VEX file.
About the LCFC software, you said that you couldn't run it remotely. You should be inside the local network.
Yes.
Why you just don't connect to the local network using some
SSH protocol. Yes, that's what the application does. It basically automates this SSH connection. It opens an SSH session, launches the correlator.
Basically, you can do it.
Yes, you can do it, but why do it manually when you can automate the process? If you can automate it, you should automate it.
Yes, I have a question about the distance of the telescopes and then right preciseness of the measurement. Can you describe how much precision you will get from how much distance?
I don't remember the exact formula, but the thing is, the greater the distance between 2 telescopes, the greater the precision you get.
So it doesn't matter if there are like some other telescopes in between the two. I mean, is it better to have 2 or just like 100?
Only the wait a minute. Well, the more telescopes you have, the better. So, yes.
So for the current system, you'll be using ground stations. But are there any advantages towards using a satellite-based system? Taking measurements from in-orbit satellites,
You mean, what are the advantages of antennas on the ground instead of using telescopes in orbit? Well, that's a good question, actually. Well, I'm not even sure. Well, it's cheaper, I believe. That's
maybe advantages towards using satellites instead of ground stations.
I don't know, launching a satellite seems like a more tricky task than observing something from the ground. If something happens, you can fix it immediately. And a telescope in orbit, well, it's not that simple. It complicates things greatly. That's my opinion. Just my.
I'm sorry, maybe I didn't understand. You said it's not used, it's not still used on the telescopes?
No, I mean the application is not running currently.
The application isn't run, but this BLBI is used on some telescopes?
Oh, it is used on the telescope in Ubene and other telescopes. Well, yes, it is used.
Okay.
If you mean it's generally used, yes, it is.
Okay, thanks.
Thank you.
Thank you.
So, the last one.
So my name is Yanis and I will talk about detail about application that I and Felix developed in this summer. So next, task for internship. The task was to develop an application for automated data correlation for EVLBI, and to do that I need to read about materials about VWL. In the end I need to create a user manual, so after this application is deployed anyone can use, no matter so yeah. And the aims of application, so basically now you need to do many tasks manually, and the aim of application is automate everything. And we achieve most of the tasks. That one task is not achieved, that we have the two servers. One server stores the data after observation, and another server correlates the data. So what is not done yet is that sending data from that server who stores those data after observation to server that correlates those data. So that's one thing not achieved. And other things that's not achieved is that we plan that user can view previous experiments and change data in control file and correlate again and see the difference different in the outputs. So that's not achieved. And other things what we plan for this summer we done. And now I will show that some technologies what we use with, as previously mentioned, we use SSH and SSC to send data, to execute commands remotely. We use Spring Boot for created REST IP. We use MySQL to store data. We use Gradle for dependency management. So we use Angular, Bootstrap, and to create a dynamic web page, to create SPA application, and so on. And next one I'm going to show that some screenshots for application. The first thing what user needs to done is authenticate. So top picture is authentication form, bottom picture is registration. If users are not registered, can register, then admin will register him and he will get email he are registered. And of course, the user can change password if he forget a password, and everything is secure, every password is encrypted, so no one can, if someone accesses the database, there's no use because he sees encrypted passwords, and that is handled by Spring Security. So, and next slide is about Vex upload page. So it's very simple. You just choose file. There are two options. User can check that box, add the clock box, and that, well, what that do is user will need to manually add date for the clock block in Vex file, and other option is non-check, and then the application will do it for. And next slide you can see form for create a control file. The thing first user do is choose a scan, and then when you choose a scan you see all the stations for the what is participating in the scan. When you choose the stations you can specify the directory where are the data source for that station on the correlation server. And when you enter all the data, the control file is created. The next thing is start the correlations. And in this step, you can check the Vox file if it's created correctly. You can check the control file if it's checked correctly. There is one thing, the mixing going back if something is wrong. So that thing still needs to implement in there. And when you press that button, start correlation, there are two things what can happen. First, error can be, for example, if you specify wrong directory for data source, then the correlator cannot find the data source and there could be error. Another thing is if everything is correct, the user will see the graphs of result. And here's the example of error. If user sees this error, he knows that something is wrong, either the Vex file is somehow wrong, control file is wrong, and one thing he can do, he can ask to system administrator who can access to that application server and can view the logs and give some more feedback to that who runs this correlation. And the next thing is example of graph, and in the ideal case there will be only one spike, and this is two spikes, but it's not too bad. You can, and one thing what it didn't do is that we cannot map the baselines with graphs, so you see that station 1 is 0 and station 2 is 0. There should be for them there should be AF for Esselsberg and not zeros and something like that, or yeah. Next, what we did, we created a little demonstration how our application works. Yeah, you can see that you can log in. After you log in, you can upload Vex file, and when you upload Vex file, then Vex file is parsed, and its application gets all the data from Vex file, and then you can create a control file. And there is the choose of stations and channels, and you can see that you can immediately when you select the stations, the data source input field appears, and you can specify the data field. And later in the video, you will see that another station is also selected, so another input field for the stations appears. So in this moment, the reference station is chosen, and immediately you see it. And now you see that animation, this is while the correlator is working, and animation usually will be longer, so we cut some parts out of this video. So in there you can see the plots, and the option is you can go forward and you see previous plots and next plots, and if you're done, you press close, and in the end you can press log out. I can get ending back to the presentation. And next slide. So, in conclusion, what we've done, we manage the application can remotely start the correlations, show the results, and the thing we built will continue work for this application in next month, and we will try to map the baselines with the graphs. And another idea what I had, we can make a map of the object that is absorbed, and that's the future work. And then thank you for attention.
Yes, sir.
What kind of security or encryption?
Oh, that I said they use Spring for REST IP, and that's handled by Spring, and I actually don't have an algorithm for that. And
Do you know how many bits it is?
what?
How many bits encryption is?
Oh, I cannot answer that. But it's what it does. Well, for same password, if you crypt it many times, it will give different decrypted password. So it's secure.
If you're using the default Spring Boot security, it's 256 bits. Yes, I suppose.
So you are encrypting the passwords, not hashing them.
Yeah.
That's all.